Nevertheless, I think we start because we are already quite delayed in our schedule. So the main new topic of yesterday was the synchronization stuff. And well, for the first, this metastability issue, there's hardly anything to be recapped. We just derived the formula for this mean time between failure. And well, we can apply it to some flip-flops. What is maybe interesting to us is we have a time window, T0, that is critical, that we don't have in hand. That is something which is given by the technology. We have a data rate that we can theoretically impact. But if we reduce the data rate, that means we take longer for the overall transmission, so we will not win anything. We can also try to impact the clock speed of the receiver clock. That, well, can have a little bit an impact, but at the end, we run a system on the maximum clock usually, so we don't want to reduce this. Then we have here a parameter TR, which is how long are we allowed to take to resolve the critical state. That we can impact up to a certain extent because it may depend on, do we directly connect our flip-flop to some gates, to some logic, or is there just a next flip-flop? And then we have a parameter tau, which is again a technology parameter we cannot. So we can hardly influence this mean time between failure for a single flip-flop. That's the main message here. And well, what was the solution to get a higher mean time between failure for our system? So assuming this is the mean time between failure that causes some logic error at the end. What was the idea? What we can do to resolve this issue with this too short mean time between failure? In other words, what was the solution for the metastability issue? Synchronization. We put a synchronizer, and the synchronizer is just, we put a series of flip-flops. It's kind of a, let's say, shift register. So the solution actually on a circuit level is pretty simple. However, increasing this synchronizer chain, flip-flop chain, makes the timing worse because we need more clock cycle until the value, even a valid value, propagates from here to the logic. So we have wait cycles, and each flip-flop adds to the area. So usually you would say 2 to 3 flip-flops are enough, but if you fear maybe my system is not good enough, then you can add another one and another one and another one. But usually 2 to 3 should be enough. Okay, that was this part. And then we talked about this transmission of multiple bits. There, effectively, one point is we do not want to put a synchronizer for each and every data signal. And we do not want that the data which are received here are different from what is sent. So we can put some synchronization on an enable signal. So if we send data here and receive them on the receiver side, then we only synchronize the enable signal, and we ensure that the data here are stabilized when an enable signal has propagated through the receiver clock. So if we send the data here, let's say with the sender clock, 1 clock cycle earlier, then we put the enable, then we can be certain that if here the enable is synchronized, is delayed, then when the enable signal arrives here at that point, we have here a stable signal. Stable signal at the input means we have no problem with synchronization. We need no synchronizer anymore. and therefore we do not need a synchronization circuit here, but we only put a multiplexer. And this multiplexer is configured so that as long as the enable signal did not arrive, we store some data here. When the enable signal arrives, then we enable here the input pass, this one here, the black one, and take in the valid signal from the data pass into this flip-flop. Huh? So now we have effectively a way to transmit an arbitrary-sized data word from a sender to a receiver. Huh? And the only problem that remains is that we do not know on the sender side how frequently we can send a data word, right? Makes sense? Yes? No? Good. And for that, how did we solve this problem? So, exactly, we need some handshake protocol. Huh? So, we have a handshake protocol where we say on the sender side, now we send something. On the receiver side, okay, we have received the data. Then we sync back to the initial state, and we know that the transmission was successfully completed on the sender side, and the receiver always knows if the data are available. Huh? And your data here can, with the synchronizer on the previous slide, came in arbitrary size. Huh? So, problem at that point solved. An alternative to that, or effectively bringing together this handshake protocol with such synchronization at the end, brings us then to this FIFOs. And, well, that was just a description. On a high level, we had two FIFOs. The first one was this one here, this fall-through FIFO. What is the basic principal concept behind this FIFO? Generally, a FIFO is first out, a little bit more targeted on DIT one, on this architecture. So how does this work? General concept, so not logic-wise, but just from a general idea. So let's maybe start with what is data pass, what is control pass. The write belongs somehow to the control pass here, yes. So this is my control together with this full clear empty flex. Yeah? The overall control part is this one here. Yeah? That's my control path. Yeah? With this, with the lower half, I control effectively what happens in the circuit. My data path, so where I want to store and read and write data, is the upper part. And now the upper part are effectively ledgers, and the ledgers are initially all, let's say, unblocked or all blocked. No? So we cannot write anything. Now, the process is we apply data here, and then we put here some write. And if we put here some write, then we have, let's say, a sequence of spikes. No? So very short pulses, which shortly enable here this ledge, then this ledge, then this ledge, then this ledge. Because the signal propagates just because of the timing of the gates from left to right, and due to its propagation delays, enables one ledge after the other. Yes. If it arrives on the last ledge, just by design down here, this one here is locked, and the next data word that we write here would only propagate till here. And so on, the next bit till here, the next till here. If we do not read, then at that point we would trigger this full flag. If we read, so the first thing also triggers this not empty flag. If we read, when they are there, the data are there, then we receive here, we unlock, or we first, with reading, we take the value from here, from the data that's already here. It's already permanently at the data output, so that's already there. But if we trigger now the read clock, what we do is we unlock this stage. With unlocking this stage, that unlocks the stage before. We propagate the data word from here to here, then this one here blocks. Then we propagate from here to here. So the signal effectively propagates now from right to left. Huh? And by propagating from right to left, we override with the data point here, this one, with the data here, this one, with the data here, this one. And then our full is released again. Yeah? And we can write the next data word if we want. That's on a high level what happens. Okay. And the propagation is then visualized on these slides, a little bit lengthy, to be honest. Okay. Or maybe I just go back to have the picture there. What is the drawback of this? Why did I say this is actually not how today you build usually a FIFO? What are drawbacks of this construction? So, I mean, it's a nice thing, right? It works. It is quick because we are not depending on any clock. It's just as fast as the propagation delays through these ledgers. Nevertheless, usually today we do not build it like this. Huh? Any idea why? Yes, the size is one problem. Another point. So you have the critical path effectively so for the first data word, you have the propagation delay from input to output, which might be longer than needed. Yeah? So this critical path increases with the depth of the ledge. And the third point is, this is of course very critical regarding timing, right? So you need to ensure that the spike that you have here is long enough, but not so long that maybe this one here is still enabled when you write the next one. Yes, otherwise you overwrite several of the data words what you don't want. Yeah? So it's at least semi-custom design where you have a lot of handwork to do it. Yeah? That's another problem here. Good. So what do we do instead? Yes. So we use this static memory flip-flop, which is on the right-hand side just the process visualized. Yeah? We interpret a dual port RAM as a ring, and on this ring we put a pointer like for a watch. Yeah? One for the write, one for the read. And if data come in, we write them somewhere and increment our write pointer. In that way, we ensure that we are always one address ahead of where we should write. So that is okay. Then we have the read pointer. The read pointer, points somewhere and applies always to the output this value. If we want to read, we read the data, apply the read signal, and increment the read. When are we full? Well, we are full if the write pointer reaches the read pointer. When are we empty? We are empty if the read pointer reaches the write pointer. Huh? So that's pure logic comparator of the two counters here. Huh? So if the write pointer comes here, then we have written everything, but I have not read this point. So we are here with our write pointer. Then we have to say we are full. We cannot write another word, otherwise we would overwrite here. To avoid that we do this just, well, by mistake, there's a write control involved that blocks effectively writing that. On the other side, we have the read pointer. And the read pointer, if this read pointer effectively reaches the point we have just written, then, well, if we try to read the next word, it's empty or it's some data from a previous write that is not yet valid, or not valid anymore. So we need to say, okay, we are now empty, and we trigger here that we block effectively further reads. Okay, that's not very difficult, right? Quite straightforward. And the simplicity of the design and that it scales well makes it actually the choice today. So you have just a piece of SRAM. That is something you can just put on your chip. You have two counters to implement, and you have this little bit of logic here. So still as that, this is an asynchronous FIFO. So in which sense is this asynchronous? So very generic. if you say you operate a system with a write clock. Yeah? We just call this clock write clock. When is a part of the system asynchronous to this write clock? So on a very generic level, because there was no reply, what effectively makes this asynchronous? The question is, we drive a system only by this write clock. Yeah? Some clock, we call it write clock. What makes a system asynchronous to that? No? Yes. Why? So I, just as a quick sketch, I know you prefer if I draw on the paper, but it's so few that I just want to show this, make this on the table. One quick explanation. So, two cases to explain a question. So, just to visualize what I have in mind. We drive the system with a write clock. And is that correctly? The read clock can make it asynchronous. These lines here should visualize that where the clock of the first clock edges are. So this is our write clock. This is our read clock. Synchronous or asynchronous? Synchronous. This one here is a read clock. This is still the write clock. Asynchronous because it has a different frequency. This one here is the read clock. This is still the write clock. Asynchronous, we have a different frequency and different phase. Different phase alone would be sufficient. So why do I say this is an asynchronous FIFO? Because potentially the read clock can be this one or that one. If this is something asynchronous, then this read controller, this read counter here is asynchronous. The data read is asynchronous to the write domain. Okay? Because we read our system here, the read domain does not know about the write domain. If this clock is different from that one, we read with another frequency at other points in time than the ones which are synchronous to this clock edge. Okay? Make sense? So, if we now have this case, what can happen? We write something into our system. Our status of the system changes from empty to full, to empty to not empty. Yeah? We read in the read domain this signal, yeah? This empty signal. By chance, our empty signal has a transition, let's say somewhere here. No problem for that case if our clock is just offset, but a problem if our clock is not synchronous, not synchronized with the clock edge. So this asynchronous clock, in that case, we don't have a problem. In this specific case, here we have already a problem because we are somewhere in transition. We would propagate an possibly metastable state into the read domain. Okay? Now I'm just saying if they are not synchronized at design time. So what is the general problem maybe? Maybe a step one, before I go to this, a step once back to once again explain what the actual problem is with this asynchronous things. So you remember we said if we have different, if we have latches between our logic, then we would have to consider the complete timing. Why is this? Because we have not enough information in design time, at design time about the individual intermediate steps. So now you have two systems. System A, whatever it is, transfer, system B, whatever it is. Very generic, any circuit, any logic, maybe a complete chip, doesn't really matter. As a designer, you're responsible for system B. You know system A from a specification perspective. So system A, we know the specification, we know at which clock it runs, but we do not precisely know at which point this here started. The clock that goes here is another one than the clock that goes in this system. So you can synchronize all your flip-flops, all your internal stuff on clock 2 can perfectly compute all the timing in your circuit, and all is good because you respect your setup and hold times. We are in a kind of a perfect world. Now, this ugly guy from A comes. This guy is also in a perfect world. All he does is synchronized, is perfect. But now they output something with a clock that is this one. And you receive it with a clock that is probably that one. You can, of course, try to transfer here this clock signal. Yeah? So you can say, I send here a right clock. Yeah? If you do this, and system B operates fully on the right clock, you're fine. Yeah? You remove this here, put this here effectively here, then the two systems are synchronized. Works. But frequently you don't want this. Huh? You have your own system on your own frequency, probably a completely different frequency from that one. You still may decide to transfer this clock, but internally you want to operate on a different clock. Huh? So now you need to come from that clock domain into that clock domain. This is where the synchronization happens. And we have now here the case that the write clock comes from here, and the read clock comes from here. Here's effectively where your FIFO comes. So your sender can send data, and you operate with your own speed. You don't care actually what this guy here does. So you're completely decoupled. The only thing you need to do is you need to say this guy at some point, hey, stop, I'm full. I cannot read anymore. Because then this guy is also completely decoupled from you. That's the overall idea of this FIFO stuff. Now back to what is synchronous, asynchronous. We have here this write clock. We write data. We trigger with the write data here the not empty signal, because here as a system B you need to know there is something available. But this is exactly the point where you cannot rely that the clock that comes from here and the clock that comes from here, which triggers effectively the logic. So there is kind of a logic and a flip-flop that tells, okay, if data written, if this comparison is something, then trigger the not full flag. And this not full flag is now, because it's triggered by the write process, not synchronous in the read domain. So that is a point which is asynchronous. The second point this is asynchronous is we generate on the system B, we generate here, if we read all the data, the empty signal. Or not, at not full signal, right? So if this not full signal is set from B, it should be evaluated by A to continue writing. So if A evaluates something generated by B and doesn't know at which point in time the signal actually is generated, there is a chance that you take something on the edge, which causes metastability issue. So you have this asynchronous behavior here, right? Makes sense? So overall, the not full signal is triggered by a read operation, so and evaluated in the write domain, asynchronous in the write domain. The not empty signal is triggered by a write operation and evaluated in the read domain. For the not empty, let me just think 1 second that I do not say something wrong. So the signal goes not empty if something is written. So it's written in the write domain and evaluated in the read domain, right? For the not full, then maybe I mixed this, sorry. For the not full, it is you read the last data, or it is set if it's full, of course. Yeah? But if it's full, that is triggered by the write domain. The reset is triggered by the read domain, because you read something, then it stops being full, right? And this read triggered signal is evaluated in the write domain because the write domain needs to know if it's full or not. Make sense? So you have, effectively, you have a stable, your memory, and if you reach, so you are here in the write domain, and the read domain, this here is the write domain, you start writing. Yeah? The first write operation triggers here the not empty, so let's say E not. Yeah? This is triggered by this first write. Yeah? Now you continue writing. For simplicity, I do not read. Meanwhile, you continue writing until you reach the highest address. Yeah? So the nth address. So then this sets the, I just call it full signal, or resets the not full signal. You reset the not full signal or reset the full signal. Yeah? I'm now full. Yeah? This one here is evaluated in the write domain, right? This one here is evaluated in the read domain because I need to know on the read domain, can I start reading? And I need to know in the write domain, do I have to stop writing? Yeah? If it's full, you evaluate in the write domain. Yeah? If it's empty, you evaluate in the read domain. Yeah? In that case, the critical is the first write. Yeah? Because the first write here may be asynchronous in the read domain. Okay? Now we start reading. And while I read, for simplicity now, I neglect that we can also write. Yeah? So we do not write in this time, just to have the signals more clean. So we read signal n, or actually we start reading at the button here. Yeah? So we start reading here. This here triggers the not empty, not full signal, which is evaluated in the write domain, because we now can potentially continue writing. This is critical because something triggered by a read domain clock is evaluated in the write domain. And then we go further. We continue reading. At some point, when we reach n, as long as we don't write in meanwhile, if we reach n, then now we have to trigger the empty signal. This is triggered by a read clock and evaluated in the read domain. It is okay. Yeah? It is not critical because this is synchronous. Right? So if you go here, so if you continue reading all your memory until it's empty, the empty signal is triggered by an operation, a read operation in the read domain. Yeah? So this is an uncritical case because this empty signal is already synchronized. The empty is always evaluated in the read domain. The full is always evaluated on the write domain, but the full can be driven by read and write, and the empty can be driven by read and write, depending on in which state we are. So it is, the full is once here at the beginning, the empty is once here in the beginning driven by the write domain. Yeah? So this here is by write. This here is by read. This here is an uncritical operation. This here is, I just make it like this, is a critical operation.
In the write domain, not full write domain, but triggered by the read.
You see? So, full is evaluated in the write domain, yes. Okay. Empty is evaluated in the read domain, yes.
Empty is evaluated in the read domain, but triggered by the read domain.
Empty is evaluated by the read domain, but might be triggered by the write domain.
Isn't this not empty?
It's the same signal, sorry. So.
Oh.
Yeah, so you have effectively what we have is we have on that side, we have one signal that goes out to so the full signal would look like we have at some point we are full, and then if we read, we go down. The not full signal is just, it's one and goes down. you would not wire twice. You have one of them, and then you evaluate accordingly. So, in that sense, you have only one of them. And I could also write here, effectively, this is not full, and this is not full, and this is not empty, and this is not empty. So, if it's the empty signal is reset, the not empty is set, that is an operation triggered by the write domain, evaluated by the read domain.
So not empty, but triggered by your.
But can be triggered by the write domain. Okay. It's not in all cases triggered by the write domain, but in half of them. And full the other way around. Okay?
So then for the write domain.
It's evaluated in the write domain, can be triggered
by read domain.
In the read domain.
Okay,
yeah?
Then for the empty is evaluated in the.
Empty is actually exactly the same as non-empty, and full is exactly the same as not full.
Oh.
Yeah, it's just, well, what you would implement is only one of them. So you would not implement full and not full because it's the same signal. Yeah? It's just one inverter away. So an additional wire is more expensive than putting an inverter if I need it. So yes, if you write and read with, let's say, the same clock speed, you're right. You would never be full. If you have a good design, you can consider your operation speed of the receiver side, your write speed of the write side, and you can design your FIFO ideally so that it's never full. Because then you can run it on the maximum speed. But let's say this is a sensor sending data to your main system. This is a microcontroller. Yeah? You do not know when data arrive at the sensor. Yeah? It's just a sensor. It's somewhere out there, and it sends data whenever they come. Right? The microcontroller has different jobs. It does not only evaluate this sensor, it also evaluates another sensor. It also has to communicate with your, don't know, smartphone, and so on and so forth. So if data arrive here, the FIFO will tell your microcontroller, hey, here you have data. The microcontroller then says, either, okay, give them to me, or the microcontroller says, nice that we have them, I need them later. And you cannot know at which point in time you effectively start reading here. Even if this here runs on a higher speed than that one. That's the first case. So even if they run on the same clock, that are different systems, you are not necessarily can rely that all data you send from one system to the other one are immediately processed. Then you need kind of a buffer, and there you use a FIFO. The second thing is, if they run on different clocks, and by chance, B is on a lower clock than A. So we have this case here, right? The write clock is much faster than here the read clock. So it's twice the speed. So I can write 2 data words before I can read 1. So I need to be able, or I can reach a state where the FIFO is full, and I have to wait here with the fast clock before I can send further data, because this is just slower. I can also construct the other way around, that my write clock is slower than the read clock. Then I always need to run to the empty. I will never be full, but I always run to empty. Okay? Okay. Good. So to avoid this, what we can put is we can put some synchronization just into these read signals. If I want to include the synchronization into this FIFO, then I have additional requirements, because if I want to synchronize, this implies that I have a permanent clock. Only with a permanent clock, we can see that there is some data. If we would have here some clock that is only triggered by the read, only if we read, we would update the full empty signal, and that's not what we want, right? So to update this full empty signal at the outside world, all the time it changes, we need the clock from the respective domain. So if we want to read, for instance, the what did we say? The full signal is evaluated in the write domain. So we need to synchronize the full signal with the write domain. The empty signal is evaluated in the read domain, so we need to synchronize this signal with the read clock. So we need a read clock and a write clock in the FIFO, permanent clock now. And since we now have a permanent clock, we also need an additional signal that triggers when a write and when a read should actually happen. Good. There's one other thing that can get asynchronous, which are effectively the counters. So to generate here the logic, to generate here this full empty signal, we need to compare here if this here is larger or equal, right? Because we said, so maybe we write it like something like this. So this is actually what triggers our logic flag, right? So we compare, we have said we are in the cycle, right? Where we have a read pointer and a write pointer. Read pointer and write pointer are counter, read counter and write counter. And we ask the questions, are we larger, smaller, or equal? And this decision triggers, are we full or are we empty, right? So the write counter is driven by the write domain. The read counter is driven by the read domain. That means these two counters run on asynchronous clocks. So they're driven by asynchronous clocks, and then we form a logic on asynchronous clocks. That can, in the worst case, cause something that you release, for instance, just because of runtime issues in the counters. You release your, empty signal, not empty signal. Also, you are still empty. Or you release your not full signal, also you are already full. Yes, so if you connect the two counters, you compare the counters directly, you have a chance that by this transition in the counter, you trigger signals that are not correct. Why is this? Because if you count, so let's say we have a binary counter. Binary counter, well, we start to count from, let's say we are currently at an address 3-bit, which is, let's say, 110 with one of our counters. Doesn't matter with which one. Then we increment. The increment is just 111, we add 1. We increment another time. Now, the outcome will be 000, the thing overflows, right? But from here to here, there's analog behavior, right? So in between, you will see something like 110 because the first bit is already evaluated and the carry propagates here. 100, this is already evaluated, the carry is still in propagation. And then 000, so you have some other values in between which are different from this one and that one. And this can cause, by the comparison, that for a short time you have a peak here that is just wrong, right? So the comparison might get wrong. That you can also fix based on the counters by implementing here some gray counter. We will talk about gray counters later, so I just skip it for you. Good. I think that was this part. Then what is open still is the synchronization first. Synchronizer, the reset, that we did not talk about yesterday. For the reset, we have two cases, classic cases again. We can have a synchronous or an asynchronous reset. To give you quickly an idea what happens, I can do this, I think, on a visualizer. So we have a system where we have some reset input. If you implement a reset for an input, would you implement a signal that is, let's say, initially 0 or is initially 1. So if it's active 0 or active 1. Active 1, active 0, yes. Why? Yes. So if you start up your system, you automatically go through reset. You don't have to do something separate. Yeah? So now we have this reset, and this reset in your system goes into different flip-flops. Yeah? Each flip-flop has some input-output. I just draw them randomly here somewhere. Yeah? Then we have here one, and we have another one here. Yeah? This is our, let's call it reset tree. Yeah? So the reset is distributed to different flip-flops. Yes. You try to balance this as much as possible, but at the end, it might not fully work. So let's say we have for all or for some of these points here, I call this here D3, O3, this here D2, O2, this here D1, O1. And then we take some clock signal. The clock signal, how many do I need? Maybe 3. Looks like this. And we have our initial reset that comes at some random time we do not have in hands. So probably somewhere here. Okay? Our signals D1, D2, D3, we all say should be at 1, and for simplicity we keep them just at 1. So we have the output signals O1, O2, and O3, and they are initially, I just go into this point in time here, they are initially at 0 because we have to reset, right? Okay? So here's always, this is 1, 1, 1. Okay. Now we consider a little bit of timing. Namely, we have here some capacitor, here some, here some, here some, here some. All our wires have some capacitance. Probably I draw another one here and another one here. Okay. Now, the whole point of a reset signal is that the system is in a defined initial state, right? But now what happens if we consider our reset signal here at point 1, 2, and 3. So I just draw here, just fits, R1, R2, R3. Now, obviously this is driven by our reset signal here at the input. So we have it at 0. We can go down here a little bit, it's just where the reset signal is. Now we see here a certain delay by this capacitance, a certain delay by this capacitance, 2 times the delay. We have effectively a set slightly delayed, compared to that. Then it goes up. Assuming it goes up early enough from this reset being released, we trigger that O1 is released, right? And follows just D1. The next here sees not only 2 capacitors, but the wire is longer. So we have 1, 2, 3, 4 capacitors. So the delay should be a little bit longer than what we had here, right? So we add another little bit, and for R3 we have 1, 2, 3, 4 again. So we should also see a similar delay as for the second one. Yeah? So it goes up somewhere here. Okay. Now, since we evaluate with our clock, so we evaluate effectively with this clock edge here. At that point, the signal here This one here is already 1, but the other two are 0, right? So the lower two signals here are, for the point in time where the clock edge occurs, are both 0. That means our flip-flop is still in reset. Our value here stays at 0 and only goes up for the next rising edge later in time. Which one? For R1, yes, it is. So we have a reset signal here, right? Which triggers this one, that goes up. O1 goes with the rising edge, goes up. Yeah? Yeah, that was, I think, what he said. So this goes from 0 to 1. Yeah. For R2 and R3, we said we have a tiny little more delay. So you see this grayish line, which corresponds here to this rising edge. And we are a tiny little bit behind. That is sufficient that our flip-flop stays in reset and stays 0 here. Okay? So what is the problem now? Our system here starts with a state to process where one register is already set, the other two are not set. Also, we wanted to start the system from a state where everything is set. No, you have here, so I need to go here. You have here the reset signal, right? The reset signal in an ideal world would arrive on all the points at the same time. Yeah? So if we release the reset here, it would go up. If it goes up here, it should go up here and here and here, right? So in an ideal world, everything would go up here on the screen line. But now you have capacitances which delay your signal. Okay? The first one, the upper one, where the flip-flop is out of our picture, we have two capacitors. So we have a short delay, which is this one. Then it follows this signal. It's not dependent on the clock. It just goes up and stays high. The other two have 1, 2, 3, 4. 1, 2, 3, 4 capacitors. So we have a larger delay. So it is delayed further than this one. I draw it here. That shifts it to the right of this clock edge. Nevertheless, it is independent of the clock. It follows just the signal. The reset is released at that point. Yes? No? Because there's no flip-flop in between, right? So there's no clock involved. But the reset forces the flip-flop in a state, right? Even if the clock comes. That means if the reset for the flip-flop 1 is already released, then a flip-flop does what a flip-flop does. It just toggles because the input is 1. The other two flip-flops still see the reset and stay at 0. Of course, they are impacted by the clock, but they do not know that this reset. They do not see this reset. They only see register 3 sees this reset, which is delayed. Register 2 sees this reset, which is delayed. And this reset is still 0. So why should they act? Okay? So, meaning these two do not switch, then the reset is released here. And with the next rising edge, of course, the flip-flop does what it does. It just flips. But now we have the problem, we operate here with this rising edge on a partially initialized, partially non-initialized state, right? So we process here data that are not the initial data, and this can cause, or this causes that we start actually out of a state that is that's not what we want to do, right? So we want to enforce a state where all the O1, O2, O3 initially are 1. That is how we designed the system. But this is not what happens because the reset arrives at some time which does not fit our demands. Yes? You mean because this here is 0? No. The reset is 0. Usually we have in a flip-flop, if the reset is 0, the outputs are 0. This is an asynchronous reset which goes into the register. An asynchronous reset overrides whatever comes from the clock. So An asynchronous reset absolutely does not depend on the clock, and always a reset overrides what you have on the data. Otherwise, you have no reset. Yes. If you set the reset to 0, then everything is forced to an initial state. Yeah? What's the question? Yes, that was the initial question I actually asked. If you put a reset, would you put the reset to 0 or to 1 as active state? So active state means what actually resets your system. Yeah? And usually you force this to be, or you implement this to be 0. That's not a must, yeah? But it's the usual way, because if you boot up your system, what is the initial state of a system? All 0, yeah? Because there's no power at all, yeah? So where should there something come from? So if you switch on your system, you're already in reset state, and automatically you go through the reset. Yeah? So you do not have to do something on top, that after power up, you first force everything to 1. Yeah? You first force everything to 1, yeah? Just to remove this 1 later. Yes, you do not have to implement an additional logic to force the reset to 1 initially. Yeah? So that's why I start here with the reset forced to 0, because that's the usual way to implement it. Yeah? You can also implement a reset that is active 1, and maybe that's a good chance to tell you that this is a frequent mistake in many designs, that one half of the group tries to implement a reset at 0, the other half of the group tries to implement a reset of 1. Both test independent, both systems work perfectly fine, you plug them together, and at the end nothing works, because always one of the parts is in reset. Yeah? So it's a critical point indeed. Yeah? Okay, now why do I tell this? So one problem of this asynchronous reset is that at any point in time this can come. It is not dependent on the clock, and it may come to an unsuited time, let's say, yeah, where we have afterwards half of the system in reset and other half we have not. We can try to improve our timing there, yeah, to make this very similar. But even if we push as hard as we can, we will not have it perfect. Yeah? So this case virtually always can happen. Yeah? So what's the problem? We have effectively no control over the clock input here. Yeah? So we have possibly invalid states. Good. So what would happen if we implement on that position here just a flip-flop? Just a flip-flop. So effectively, we synchronize this. Yeah. I do not want to draw it on the paper, because at the end there's a little bit different solution. But effectively, the idea is to put it here. Yeah? So you have here your external reset, here your clock. Huh? Yes. This part not really, because you have the delays, yeah? But at least this one here. Yeah? So what would happen in that case? Exactly. So the reset, I go to this picture, yeah? If you release the reset at some point, then only with the rising edge it's propagated into the system. So now that means I have one clock cycle to propagate this internal state to all of the registers all over there. I can do timing analysis and can check, is my critical path to the system short enough that all the registers are supplied early enough before the next clock edge. So I'm sure I'm now in a synchronous way. Now you are in an automotive scenario. Yeah? You drive on a highway. This thing here controls your brakes. Yeah? And a stone comes, damages your car, your clock is broken. What happens? You try to reset the system to be able to brake. Yeah? That's your safety state. What happens? You continue with the last internal value, you continue processing, you cannot reset your system. Why not? Because your reset depends on the clock. Yeah? So you cannot propagate the reset into the system, because it depends on the clock. For a safety critical system, bad idea, right? So we have, that's where I probably go back to this one here. You have two cases, two possible designs. In principle, you have some asynchronous flip-flop, asynchronous reset, or you have synchronous reset. Synchronous reset means effectively the input of the data is ended with the reset, and then the reset comes with the clock. This case here is similar to what I've drawn with that one, just that in that case we synchronize only at one place, and here we synchronize for every flip-flop individually. So this is the standard case for an FPGA. This here is the standard case for an ASIC default. Benefit of this one here, you have here, if I put a reset, I immediately reset the system. This is nice because I do not depend on any clock. I have not any delay. If I want to run time critical into a reset state, this helps me. Yes? So this one is the usual case you implement in an ASIC, every individual flip-flop. This one is the case you implement usually in an FPGA, every flip-flop. The usual, not the necessary. Yes. What happens in this reset is you may have unintended resets, because if there's a glitch on an asynchronous signal and you immediately reset the system, a glitch on your reset would cause a reset of the system. The second is what I had drawn. That's the, I would say, more critical one. If you remove the reset, if you reset, your system may go into an undefined state because of this clock issue, at which point in time our clock actually comes relative to the release of the reset. On the other side, we have this synchronous part. We have the benefit that now we have plenty of time to release the reset to the complete system. The system is, from a time perspective, much better. We also have not the problem that there are any glitches, but there's a chance that we can miss a very short reset. And we have the problem in a safety critical system, if the clock is broken, our reset doesn't work anymore. So both has benefits and drawbacks. Raises the question, can we do better? And indeed we can, because, well, yes, I start with this, because here the critical case is that the reset, no, other way around, the benefit is that the reset, so pushing the reset is the critical one. So setting the reset to 0 to our reset state. Here the critical case is, or the good case is, the release part. So these are two different edges of our reset signal that are beneficial. And now we can combine the two. For the other things that I bring here in the next slide, for the other two things, you would go for an analog design typically. So to avoid that you have too short pulses or too long pulses, you would just go for an analog design. So what we can do is we can put something called a reset synchronizer. And probably I just directly draw this onto this visualizer thing. Maybe here and here. So I start with the second flip-flop. So we have one flip-flop here, D and Q, and then we connect this here to this reset. We connect a global reset to here, and we connect a clock signal here. So what would happen now? So assume D is 1. So it's not fully what we have on the slide, so I do not want to put here 1, but assume we just put here 1. What happens to our circuit now? Let's say we are in a state where we want to reset our system. We trigger the reset, so pull the reset signal to 0, that triggers the reset for this flip-flop, which immediately, because it's an asynchronous reset, immediately propagates into our system and resets the complete system to a default state, right? Now we want to start off from this initialized state and release the reset. Now releasing the reset means this flip-flop is put into action, a clock arrives, a 1 is put here, so the 1 propagates into a system, but it propagates with the rising edge of this clock. So we have now an asynchronous reset and a synchronous set. So reset is asynchronous because it directly propagates without clock into a system. Set is synchronous because if we release the flip-flop, we wait on the next rising edge before the 1 is propagated into, right? Okay. Now, this looks like that. Here I have another flip-flop. Why? So, we know if we are unlucky and we arrive here on some intermediate state, we may fall into a metastable state, right? How can this happen here? This one here is perfectly stable. But clock and reset are asynchronous. So if by chance clock and reset edge arrive approximately at the same time, we have a chance that the output falls into a metastable state. So what do? We remove this one here, and we put another flip-flop here before, put the one here, put here our clock, and here another reset. So, why is this better? Yes. If there is an invalid state on this flip-flop, we have one clock cycle to resolve this metastable state. In the next one, this here is stable, the clock arrives, all good. So this is why we put this flip-flop. If this is not good enough, we can put another one. Okay? This construction is called reset synchronizer, and from my perspective, the best we can actually do. Because set is synchronous, reset is asynchronous. We have no problem that we may start off from an invalid state because we can well compute the timing. And we have the benefit, we do not depend on the clock with the reset. As soon as we push a reset, it's there. Okay, then I think we make, don't know, 10 minutes break. So, and continue at 50. So, okay, let us continue. Now we have effectively everything in place to do some communications, and this I only want to make relatively quick to give you a little bit of an impression where this becomes relevant and how you do effectively then an actual communication with the system from the external world. And there are 3 main protocols, serial main protocols, that are virtually always used in the different embedded systems designs and the different ASIC designs. The first one is called UART. Did you come across this already? No. So UART is very simple. You have a protocol that says we have some asynchronous signal with a specific time slot for each bit. We have defined, per definition, that we start every message with a 0. We have then a specified data length, most of the time 8 bits, but you can specify something different. The system needs to know and needs to be configured accordingly. Then we may have one additional bit at the end, which is defined to be a parity bit. Parity bit means just, or is it clear what parity bit means? Parity bit is just even or odd. So, you can also define if this flags even or odd, that it have a degree of freedom. And then you have one, at least, stop bit, which needs to be logic 1. That's effectively this one here. So, that means if you look into your wire and you observe it, it's driven to 1 all the time. And if a message starts, it's pulled to 0. Then some bit sequence follows, and then if it goes back to 1, you know this is the word is ended. It can have any value. And that's actually the problem. You have how to figure out what you transmit. So this can be, for instance, it can be here a 1, then we have 2 zeros maybe, something like this. So that would be maybe 1, 0, 0, 1, 0, 1, 1, 0. And then we have maybe, if we say parity directly, 1, 2, 3, 4 bits. So we would have 0 as an even number of ones. So just as an example, can be, of course, any value. That's why I fill the complete block there. Okay. Now how to figure out what we actually have, because we send asynchronously. Yeah. No, you start with the transmission. So time goes from left to right. The first bit that is transmitted is the LSB. Yeah? So why do you do this? Because we will later see also for adders and multipliers, if you first transmit the LSB, you can immediately start processing. Yeah? If you first transmit the MSB, most of the time you have to wait. Yeah? So this is why we usually start any transmission with the LSB, or least significant byte if you operate on byte level, or least significant word, or whatsoever, but you always start effectively on the left. Yeah? And if you have here time from left to right, then we start with the LSB. Yeah? Okay? So we start just with the lowest bit to transmit. Okay. Now, which problem do we have as the receiving side? Well, we know how long this should be. That's a kind of a specification. We know how many bits are transmitted. We don't know at which point in time this here comes, because it's asynchronous. Huh? So we need to find this point. What would you guess? How should you sample this signal in order to find out at which point in time the first thing here comes? Flip-flop you would need to store, but how to sample it? With which frequency? Yeah, but which frequency should the clock have? So you may, if you want to have a concrete number, let's say this here is 1 microsecond. You can also say period length, and it's easier, and you do not have to divide. So probably you remember Nyquist criterion? Nyquist criterion? So if you want to reconstruct a signal, you have to sample at least with a double rate? No? Okay. So, so effectively, if you want to reconstruct a signal, I think you have at some point you have some signal processing stuff, and this definitely comes. If you want to reconstruct a signal, you need to sample at least with twice the frequency. So meaning, if I want to sample here something with 1 microsecond length, I should sample with at least 500 nanoseconds. Why? Because in the worst case, I have one in the corner and one in the middle, right? That is the minimum. That is not sufficient for reliable data receival. Why? Because if you sample with exactly this rate, then I would see here some 2 undecided, 1 which is okay. Yeah? If I now shift a tiny little bit everything to the right, something like this, then I see 2 zeros, 2 ones. Yeah? Is this now a 0? Is it a 1? Yeah? So to which point do I belong? Yeah? So actually, ideally, we go higher. Yeah? So for reliability reasons, we go higher. Theoretically, it is sufficient to have twice the frequency of half the period length of the bit length in this protocol. Good. So one option is to try we sample right in the middle, which is hardly possible. Therefore, we do some oversampling, and with the oversampling, we are able to detect, okay, there are, well, with majority voting maybe, there are at least 2 subsequent zeros here. So we decide here's a 0. Then we find at some point there's a 1. And then we can actually already try to get better because we already know something about the length here. Huh? So we can try to go in the middle, but we can also just continue oversampling and do majority voting and say, okay, this is 0, this is a 1, this is 0, this is 0, this is 1. Huh? This is how UART works, just pretty straightforward. Not straightforward to design, because it's an asynchronous design. Yeah, the rest here comes a little bit on top. So you have then for sending, receiving, you have two options. You can have a two-wire system. You have one transmitting data out, which is TX, one receiving data, which is RX, which can be a full duplex, meaning two wires, or it can be a half duplex. That means you have here a special kind of circuitry, some trial state, where you have something floating, and if you see one of the parties pulls down this wire in between, then this party can start communication over a single wire. That is called half duplex. You share effectively one wire. From what I've seen in the last year, I would say this full duplex is more common. But this here, of course, saves you saves you pins. If you think back on the smart card picture we had before, what we have there is very similar. It is just that the clock is provided from the sender side, not from the smart card itself. And it has only one wire, so it's this half duplex. Okay, that's the first thing. If you have something like this, obviously you receive something that is asynchronous. You need all this synchronization stuff. You need some buffers and so on. The next protocol, which is frequently used, is this SPI. I called it old-fashioned and not politically correct as master-slave system, because we have very frequent in the literature, you find this MOSI and MISO, which is master in, slave out, and master out, slave in. Nowadays, you also find this, I think, as server and client. Yeah? How does this work? Well, in the first place, you see there are way more wires. But at the same time, you see we connect to a lot of clients. So we have effectively two wires, or three wires, I would say. One for clock, that is now provided by the master, by the server. One to communicate from master system to the slave. One to communicate from the slave system to the master. And then you have on this master server side, you have also a select signal where I can say, I want to talk with this, this, or that. And then I can run effectively simply on top of this system some defined specified protocol, which is my clock is pulled to high as long as I do not want to send. If I want to send, I first have to trigger the select signal for a specific slave. Then after this, I have to select or put the master in, slave out signal, or master out, slave in if I want to send something from master to slave, and the slave has to post master slave signal data if something should be sent from slave to master. So this here effectively triggers any action who wants to send, and this action needs to put data. And then this time we start with the MSB as per specification, wherever. And we start sending data effectively with the falling edge. We latch whatever is on the bus. With the rising edge, we set up the data. And this way, with 8 clock cycles, we can write 8-bit. And then we put up the clock again. These two here have to stay floating then, at least this one here, because any other, this one here, sorry. No, this one here. At least because any other slave might want to write on the same line. So you need to let this float. So you cannot drive it to any value. Yes. And then if the next write operation comes, the same occurs again. Yeah? You have this enable of the slave, and then you have write data and update data and so on until everything is set. Yeah? Simple enough. Benefit, it's now synchronous. Yeah? At least in the sense that you have transferred a clock that makes it much faster because you don't have to oversample at the receiver side. And it's pretty simple to transmit. Drawback, you have more wires, a bit more logic, but overall it's, well, simple to get. You can have this, by the way, also in some, let's call it semi-parallel interface. Yeah? So there is something called quad SPI, where you have one specific message over the SPI to configure the system, and then you reuse the select signals as data signals, and you can transfer 4-bit in parallel. That's quad SPI. Okay. The last one I want to mention is this I2C. I2C is actually, yes, I would call it a full-blown protocol, meaning you have, again, a synchronous protocol where at the time you want to send something, you enable this clock, and the clock starts to run the process. Then you have a specific control sequence where the first sequence bit is effectively a start. Then you have a specific address range. Then you have 1 bit for read-write. Then you wait for an acknowledge from the slave, so that's actually the other data direction. Then you have some payload, and then you have a stop. So if you now want to send from master to slave, you pull down a start. You say, I want to communicate with slave number this and that. Yeah? You say, I want to write to them, let's say. Yeah? Then I have here to set the bit. I wait that the slave says, okay, I'm ready. Then I send whatever I want to write, and then I'm done. Yeah? That's one transmission. Takes longer, because there is a lot of overhead, this address and so on. Requires quite some logic to implement. Has the benefit for an virtually arbitrary number of slaves, we can use only 2 wires, 1 clock and one data wire. Because if we want to read, for instance, we would use the same wire. We would say, okay, start this and that slave. We now want to read. We wait for the acknowledge of the slave, and the slave will provide the payload. And then we have a stop, and that's it. So it's smaller, but more complicated from a logic perspective. Okay? Questions to that? So you have the 2 wires, you have the clock, you have the data wire. And if the clock runs, you transmit, do I want to read or write? Okay? Pardon? Depends on the application. So I would say UART is used in most of the systems as a fallback. Yeah? So it's still very widely used. Yeah? Also, we have a lot of other things. This is very robust, this is very settled, and it's a lot in use. Kind of. Yeah? Or to transmit small data now and then, yes, to do some debugging stuff or something like this. Or the drawback of that is that it's very slow. Much faster is this SPI. And if I look into nowadays systems or nowadays ASICs that are around, you most of the time also find an SPI interface. It's widely used yet. I would not say it's preferred. So it's kind of, don't know. Yeah, it depends on the specification of your protocol, of your system. It has the benefit, what I can say is it has the benefit that it's faster. So if you want to have faster transmissions with an embedded system, yeah. I mean, if you go for a full-blown CPU, we will anyway go for some parallel protocols and for serial protocols. But if you go for embedded systems, then frequently you have an SPI for the actual communication, yeah? Or quad SPI even, yeah? So that you have a lot of, or more data at the same time. Yeah? So if speed counts, I think SPI is better than UART. For the sake of simplicity, UART is maybe simpler. I would say so, yes. Yeah. I2C is also used, but it's rather in specific cases. So if you, for instance, if you have a lot of systems you want to connect to, yeah, then here you need a lot of control signals. Yeah? And then I2C becomes much better because you need less wiring. Yeah? So if in your system specification, one of the requirements is you should have only few wires, then I2C is better than SPI. If in your system specification is your system should output as fast as possible, but we don't care about the wires, SPI is better. So I cannot say one is better than the other. It really depends on the use case. Yes, yeah, because you need more, you have more transmissions. So you see already you have here to send one block of 8-bit. Before we had 8 clock cycles, or maybe 9, I think 8. And here we have 1, 2, then here up to 10, yeah. Then we have here another one, then we have actually the load. So a lot of the things that are transmitted are overhead. So it's just slower because you need more clock cycles, because you need to transmit all this stuff before you can set the actual payload. Yeah. So no clear this is better than the other one, but it's really a use case dependent thing. But most of the systems nowadays have some UART and some SPI implemented. Okay, then let's continue with the next topic. And now we go a little bit, I would say, up in the stack, more towards the system level. Yeah? This slide set is mainly to motivate why we later then dig into adders and multipliers as the core structures. Yeah? So what we already had was we had this register cache structure a little bit. What we said was, well, if we want to be close to our system, we want to have some SRAM. Yeah? That is somewhere here. If we are even closer, then we are at register level. Huh? So we have flip-flops. So we say flip-flops. Then we have somewhere at the caches, we have SRAM. Then we may have further away, we have DRAM. If we go down, something like USB sticks, you have some form of some flash. Huh? If you're further away, nowadays you have SSDs, it's also a form of flash, or you have something like a hard disk, and even further away you have probably something bigger. Still today, some tapes or something like this, where you can store for long term. ROM has a little bit of special role. I would locate it somewhere here. So it provides the boot up code for the controller. So I would say it is similar to SRAM. Huh? You just load something somewhere, and then you load from there into the registers. Huh? So then probably you heard of, in this context, as a quick recap, von Neumann and Harvard architectures. If we have some memory, we want to put it into a processor core. Huh? And von Neumann and Harvard architecture is actually how is the control and data information put into the memory, yeah? Or how is it managed in the memory. And for the von Neumann, you have effectively control data, so control signals and data in the same memory, everything shared. One bus where you transmit the data, simple, efficient, yes, straightforward. For Harvard architectures, you have a separated data and instruction memory. So everything which is for control is in instruction memory. Everything which is actual data that you need to process in data memory. And the processor core needs to load via different buses from different memories. Enables some things so that you, for instance, load instruction and data separately at the same time in parallel. That is easier with this hardware. So there's also something in between where you effectively have in the main memory, in the external RAM, you have everything in one memory. Then you load one page into the cache. And when loading this, you split it into a data and instruction cache. You have the data in one. You have the data in one. You have the instruction in the other cache. And then the core can directly access data and instructions independently. Yeah? That's just to have a little bit a recap of what these words were. I do not want to dive deeply into this different structures. Now, if you want to implement the processor core, then, well, what do we want to have at the end? We want to run some code on it, right? You want to write some C code, then you run the compiler. The compiler provides you with assembly, and the assembly you want to run in the system. Yeah? So this here is kind of or one version of an assembly code. What does it mean? We have 3 assembly instructions, which is LW, add, and SW. So what do we do here? This LW is specified as we load a word from the right side. Right side gives the address in the memory. So S1 is an address register where we say, okay, from that address in the memory, we want to read. So this says we want to read from memory address S1, and the result, what comes back, is written into our processor register S2. Now it's available for processing. Then we have the second one here, which is, again, a load word. We load, here's 8 S1. What does this mean? So we read from memory address S1 plus 8 address, yes. So 8 address offset. It's byte most likely, because you have addressing likely on a byte level. So you read, or word level. So you read from S1 plus some value, some offset, and you write the result into the register S3. And then you have, in the next line, you have an addition. You add effectively S2 and S3, so the right side, and write the result into another register S1. And the next one, you store effectively this S1 back to the memory, and where do you want to store it? That's written in a memory address register in S0, so you write whatever is in register S1 into the memory address S0. And now your process is done, the stuff is in the memory again. As per specification, you effectively have the inputs right and the output left. But that's just specification. So to run this program, what do we need for hardware? What kind of hardware do we need to run such a program? We need some form of memory. Probably we read from a cache, so maybe SRAM, but some form of memory. What else? Memory we already have, so problem solved. Yes, maybe. Not in this case, not necessarily at least. No. So think about things we did not hear. Yeah, which we did not yet discuss. No, that can run on a microcontroller easily. CPU. What is in the CPU? So get closer, deeper in the hardware. Yes. For instance, we need an adder for addition, right? We need to implement on digital level. What else do we need to implement? We need to do some multiplexing. What else? So, from what did you know that this here is load something from memory to here? some register you will need. Yeah? So from what did you know that we need to here load data from there to there? Just because I told you, right? So what I did was kind of a decoding of what this here means, right? In the system, this will of course not be an LW, it will be some sequence of zeros and ones, and we need to know how to interpret this sequence of ones, zeros and ones. Yeah? So obviously we need some decoding, we need some kind of a state machine, yeah? Because only the state machine can tell us if this here comes, what to do. We need to have some registers, as you say, we need to have some adder, we may have to add some logic, huh? And we need, what did I miss? Yes. To make any progress here, we also need a counter. Why? Because otherwise we do not know where in our program are we. So we need a counter that points us, currently we process this line. Huh? So we need to decode, we need some counter here, we need some load store unit, something what you said is related, so some buffer, registers, to store things, to load things, memory storage. And we need some adder, and to be more generic than only having this addition, we need an ALU, so an arithmetic logical unit, which comes on the next slide. So this is what we need to implement. How such a system can look like, just to have some examples seen once, I have put here this RISC-V thing. Yeah? Not sure if you heard about RISC-Vs, but that's currently still a little bit a hype topic for architectures. So what do we have here? If we want to load, if we want to execute something, we need to fetch instructions. So we load an instruction into some prefetch buffer, so that we have already the next instructions here in place, so that we can just quickly process them. Then, from the instructions, before we can do this, we need to decode whatever comes here. So we have kind of a state machine, a decoder here, that tells us what actually to do. Then we know what we want to do. There are also general purpose registers where you can store stuff. We just ignore for the moment. If we know what to do, we process this to an LU. So there's another register, another pipeline stage between instruction decoder, ID, and execution, EX. Then here we have access to the data that we want to process. We can read-write them. We can process them. We have here another set of registers inside. And then we may have additional specialized hardware, since some instructions are just slow, such as multiplication. We may have specialized hardware, such as multipliers, to speed up the system. What do you mean by selection? This one, what do you mean? Or what do you mean by selection? This one here? These multiplexes you mean? How they are controlled? Well, you have, this here is effectively depending on the instruction you want to operate, right? So it should be controlled by the things that you loaded and decoded. So it is, yeah. Let me think of that. Kind of, yes. Well, this general purpose register is just, this is a register which is not dedicated to specific addresses or something like that. You can use it actually for any operation running on the core. And for instance, you can feed back here some intermediate multiplication results if you need to further process them. Or you can output any output from the ALU there to further process them. So that you do not have to write them back into the data and reload for another round. Okay? So this is just to give you roughly once a picture that how the processor structure looks like. So what we already have are effectively these register banks. we have already the data, the memories here outside. We have such a prefetch buffer. This can be kind of some FIFO. What we did not yet do is the decoding. We did not yet talk about this ALU. We did not yet talk about multiplier. And if you have this, then actually you have everything in place. What is here on this picture, right? So you could just do some, build your own controller, in principle. So now the core thing on in our computer usually is this ALU, which is this arithmetic logic unit, which is there to do the actual operations. Such an ALU has minimum requirements, which are we need to be able to do an addition, and we need to be able to do inversion and conjunction. That means, in principle, you need logic only for a 1-bit addition and an AND gate, and then you are done with a ALU where you can generally compute everything, every program which is out there. It's just arbitrarily slow, but it works. Usually, of course, we go for larger addition. Usually, we have more logic included, we have other stuff on top. So, what we want to have also is subtraction. We want to be able to compare, we want to be able to multiply, probably to divide, and so on and so forth. We want to be able to have several logic operations, probably some shift operations, and so on. This, we will, nearly all of that, we will discuss. How it can look like effectively is kind of that. So if you have a 1-bit ALU, then you have 2 bits input. You have an AND gate, you have an inverter. You have here the multiplexer, and now you can run every program. It just takes virtually forever because you need to process every bit individually and write back a lot and read a lot to memory. It's just an adder. Okay, so addition, multiplication will be the next part. Regarding logic gates, we did already, so a little bit, or I expect that you know logic gates. We will have a quick discussion of the comparator and the left-right shift. Quick discussion of comparator we can do right now. There is actually, the last years I derived a dedicated hardware logic. Maybe we do this in the exercise. I skipped this for this year because we are quite delayed, and what you would do in practice is, if I want to do comparison, I take the one number, I subtract the other number, and I check, is the result 0? Is the result positive? Is the result negative? And then I'm done. Then I have my comparator. So I do not need really a specialized hardware for that. I'm skipping this slide here. For the left-right shift, there we can look into. For the multiplication, we will do next week. Probably, if Jens has time, maybe he adds a little bit to this comparator because it's a nice exercise, but at the end, it's just an exercise. Good. So, left-right shift. You have a hardware, and you want to implement a shift. How would you do this? So, shift registers is an option. So, shift registers would mean you have, let's say, we want to have a 4-bit shift. So, we can implement like this, right? Now, if we want to be flexible, how many bits we shift? Maybe we want to do the cyclic, because we can easily remove some of the lower bits if we want, or upper bits. But probably we implement as a cyclic shift. So it's just a shift register where you say, I load data. Let's say we put here a multiplexer. What comes here, effectively, so this here is virtually just 4 wires, So this here is 4 wires, 4 different bits that go here, 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 okay? So with the first clock cycle, maybe I load the data. Then I switch my multiplexer to the other state, and I can shift them. And the last bit is just shifted to the beginning. That we may also drop out. I just say I do a cyclic shift because it doesn't cost more. And, well, we have it in place, and filtering out here some bits is easy. So, this is an option. If I want to do now arbitrary shifts, let's say we want a 3-bit shift. How many clock cycles in this design? 3. Or 1 for load, but we neglect the loading. So 3 clock cycles to shift. Can we get quicker? Because 3 clock cycles, we don't want to wait. So what we could try is to improve on that. We could try to just forward here, have this output also provided as an additional here, this output provided as an additional here, and so on and so forth. So we can fully wire all the different outputs to the other inputs, but that's ugly, right? So we have a lot of wires here then. So I cannot even draw them here, you would not see anything, it's just wires. Because you would have to feed back every wire to every input, every output to every input. Then you have an arbitrary shift in 1 clock cycle. So this is most likely not what we want to have. So that motivates maybe that we try to find something better. So it's an option, but probably for a CPU, not the best we can do. So what is done in reality is you have such a barrel shifter. So what does this do? You want to shift, you have input data x0, 1, 2, 3, and you have output data y0, 1, 2, 3. You have in between, you have pass gates. Do you know what a pass gate is? Do you know what a pass gate is? No? So it's a very simple kind of a gate. Effectively, you take your NMOS, you take an PMOS, and then you have here an inverter inside. Here a select signal, here input, here output. If my select signal goes high, I connect input to output. If my select signal goes down, I disconnect input and output. Okay? That's called pass gate. So it's just a switch that we can implement. You have 2 of these transistors to have full swing from VDD to ground at the output, but not so important for us. It's just that you understand this here is effectively such a gate. If we switch on that side, we transfer. If we don't switch, we don't transfer. Okay? What? Which part? This one here. So this is a pass gate. We have an NMOS, we have a PMOS, we have a select signal. If the select signal goes high, we have a channel from input to output. Because here's an inverter, we have this for both. If the select signal goes down, we have no connect. That's it. The purpose of having NMOS and PMOS is related to we want to have full swing from 0 to VDD. But we don't need to go into detail. And such a thing effectively is such a block in the diagram. So it's just a switch. Yes. So now what do we do? We say we apply our input data that we want to shift. We have a decoder that translates whatever we say. For instance, let's say we want to shift by, again, 3 into a shift of 3. So it's just one hot encoding. We just set the bit to 1. That corresponds to how much we want to shift. That disables now this here, this. All of them are switched off because this is 0. It enables this one. So if we do that, the first signal here goes to this output. The second signal here goes to that output. The third signal goes to that output. The fourth signal, goes to that output. And that way we have a cyclic shift. If we would use the shift by 2, then the 0 signal goes here, the 1 signal goes here, the 1 signal goes here, the 2 signal goes here, and the 3 signal goes here. If you have a shift by 1, signal 0 goes to output 1, signal 1 goes to output 2, signal 2 goes to output 3, and signal 3 goes to output 0. If you shift by 0, 0 goes to 0, 1 to 1, 2 to 2, 3 to 3. Yes. Yeah. I mean, more doesn't make sense, right? So, okay. So it's just the colored line enables the switches along the colored path. And that's it. Okay. So the benefit of this one is each of these things is just 2 transistors. Plus 2 maybe for the inverter. But you can join them probably. So it's a simple matrix of switches. And you can, in one clock cycle, just go through. The depth is only always one of these things. It's also quick. So that's actually the way to go. Good. Then I want at least to start a little bit to give you something on the way for the weekend. With the topic I actually wanted to end already today. Okay? So, for this topic, did you already do something on adders? Just for me to understand if this is kind of a recap partially, at least, or if this is completely new. So, for instance, ripple carry adder. Yeah? So it's kind of a recap, then I hopefully can be a little bit faster. One thing beforehand, just because students in the last years now and then had some problems with this. As a quick recap, do this on the visualizer. So we want to do a computation. We start very simple. We want to do the computation 12 plus 8 in binary. So should be simple enough. We want to use 2's complement. So what do I need to write? So what is 12 first in 2's complement? No, which binary sequence do I have to write for 2's complement for number 12? Is this 2's complement already? What is it then? So if I write this number and I say it's 2's complement, what number is it? 84? Negative 4? So, yes. What we have here, if I want to write in a 2's complement, what you say, we need to consider the first bit, right? So, if we translate this here back, what would I do? I would look into, well, the first bit is a 1, so it's a negative number. Yeah? So I would invert it, which is 0011. Add 1, then I have the positive number, right? So what we have here is a minus 4. So if I want to put this into a 12, what do I need to do? Add a bit? Add it? 5. Yes. So we need 1 additional bit. I add indeed 2 additional bits because of reasons, because we do addition, and later we need another bit for the output. We will see. So you may just ignore this for the moment. I just add this because I know we need it. So this here is effectively 12. Then we write 8. 8 should be 1, 0, 0. And then we have a leading 0 because it's 2's complement, and another one because I told you so. So now we add them up. So what do? We add these 2, no carry. We add these 2, no carry. We add this, we have a 1. We add these, we have a 0 and a carry. We have these 3, we have a 1. If I would not have a 0 here, I now have a negative number. So I need another 0 here in front. And to have everything aligned, I just put the 0 from the beginning. Okay? Yeah. So it's just to have this all aligned and to have it here all the same. Yeah? Okay. if I now want to do the computation, so we stay for the moment now with positive numbers, yeah, because it makes it a little bit simpler, then I can just consider all the bits, yeah. Nevertheless, if I now want to translate this number here into back into an integer, yeah, what would I write?